Can we start?
Okay, we'll start. You good? Hey, okay, so I gave this talk in XConf. It was an internal conference, so I decided, okay, it's important, so why not share in the GeekNight and get feedback. Um, yes. Okay, so XConf is an internal conference. So for the first time in probably 5 years, we opened it for the public. It was a 2 day event. The first day was open to public. The second day is still internal. This talk I presented in the internal XConf, and hence, yeah, I'm presenting it. So that's it. Okay, so building low latency applications. How many of us here know what is low latency? Any thought? Low latency. What does it mean to you? Okay, fast. Okay. So yeah, sorry. Responsive. Fair enough. I'll start with this one quote. It's from Henry Petrowski. It says that hardware is really fast, and it's a lot of innovation is happening in hardware space. The only innovation that's happening in the software space is the continuous cancellation of whatever hardware guys are innovating, right? That's what we are doing, right? So if you actually see, if you have programmed for DOS, that's almost you get the same kind of a performance even now. But your processor has come a long way. Your memory architecture has come a long way. But still, the app basically performs in the same scale, right? So yeah, that's the code. And that's its opinion. So and how many of you think that's true? Right. So I had this slide because we use the terms very, I would say, vaguely, loosely. It's not a precise term. When I say what terms, if you have come across terms like latency, response time, throughput, it's kind of vague, right? And we use it very. We sometimes we mean latency, but what we really talk is response time. Are they same? Right. So the easiest example I came across to explain what this is a queue, right? We know queues, right? So imagine a really long queue. So okay, so if you're this person on the end, uh, so what's latency? Latency is the time that you have to wait to get to the desk, right? That is your latency. But I didn't have a picture with someone servicing. Let's say that someone in the desk is taking 10 seconds or a minute to service whatever you are standing for. That is your service time. Right? So, what is your response time? You add the both. That is your response time if you are the person here. Right? So, we come across multiple things. If it takes 1 second to serve 100 clients, what is your latency in this case? Simple math. In 1 second, I can serve 100 clients. What does it mean? If I ask you a question, what's the latency of your system? What would you answer? Okay, you don't have to compute. If you're thinking about computing math, it's 1/100, fine. But that is absolutely wrong. And we fall into into this trap every single time, is because that's not correct. So latency is extremely context specific. It depends on what position in the queue you are in, right? Latency by this guy is not same as latency by this person. It's not same, right? That's the reason why. If you really want to know more about how to measure latency, I don't think I'm covering in this talk. There is an excellent talk by Gil Tene. He's the CTO of Azure. I would recommend you to go to Google and watch it. I have the link in the slide as well. So if that is latency and that's service time and you add up and you get the response time, then what is throughput? right? Let's say that if you add these two together, if you can in 1 minute, let's say only 10 people can be serviced by that one single queue, and I want to service 30, that is the number I'm aiming at. You actually have three queues, and that so the total number of people who is serviced by the system, that's your throughput. Am I making it clear? So latency, response time, service time, and throughput. That's that's probably the closest real definitions I can get to. Right? So the title of the talk is more appropriate if I change it as building highly responsive systems. Right? And there is not so much you can do with latency. You can only scale by horizontally, vertically, and things like that. So if you are engineering, you engineer so that your system is highly responsive. Right? One way to put it. Um, I have this because imagine you are painting your house and you're looking for what color to choose from. You will get confused because there are, I don't know, millions of shades to choose from, and the same applies. If you really want to build a highly responsive system, the choices that you have is humongous once you start digging, right? And so what really happens is that we always end up making the safe bet. So this talk, I'm going to challenge the way, and the rest of the talk is going to be, I'm going to challenge some of the safe bets or the myth that we have, and I'm going to bust them so that hopefully you can build a responsive system once you bust all these myths. Right? So that's the format. So you would have guessed it. So it's a Mythbusters time. Right. The first myth that I think we should bust is what I call transaction phobia. Right? Uh, yeah. I mean, tell me if you're doing this. Your code on the server side, it's going to get some kind of a data. You're going to run some validation. If all checks out, you're going to insert, do update, whatever you want to do with the DB, and then commit. Tell me how many of us are doing this? Pretty much everybody, right? And when I say commit, we go one level down and say when you really hit commit, it should be flash to disk because we are really paranoid. I mean, the people who actually came up with this ACID and relational databases. Uh, I mean, this knowledge is so ingrained in our thought processes that we never ask this question. I mean, do you really need to flash for every single commit that you are making? I'm not sure how many of us are asking that question. Of course, true. I mean, if you are building a banking app or if you are building something that is so critical that every transaction, when you are saying it's done, it should be really persisted, yes, that's the option. But I would like to challenge that, right? So, not all application that we are building needs that kind of a consistency. And why is this so important? Is because if you do this, you're putting the first inherent bottleneck in your system. That is, you can never ever be faster than your hardware write path. No matter what you put in, you can put in the fastest SSD, you can put in the fastest NAS, and whatever it is, right? That is your bottleneck. Right. So the second myth. So the myth are not in a random order. It's in an order I think would make most of the sense. So they actually build on top of each other. How many of us here use in-memory data structures, queues, whatever? Anything in memory? One, what do you use? Redis, okay. And cache Redis. And anyone else? Any other choice? Any tool? What do you do? I want to do something in memory, right? Your program has to run in main memory. Yeah, you don't have a choice. But do you have data structures in memory? No. Caching. What do you do for caching? Yeah. How do you session? How do you manage your session in cache? Right. So you're using map in Java to cache it. Okay. So I have this picture to say that you don't have to be that tall to use in memory data structures for yourself. Uh, so I don't know if you're thinking Don't reinvent the wheel. I mean, Redis, Memcache, they've solved the hard problem for you, right? So if you have that question, I just have this picture for you, right? If someone says, please don't reinvent the wheel, you can look at that, right? And I have a reason for that. There are a lot many things that you can do once you understand. It's not that hard to have your own structures. Yes, you can live with map, but if you're stretching beyond a JVM, maybe you need a distributed map, right? And so the problem with Redis and Memcache is that it is actually another layer of abstraction. It's a network hop away. Maybe you make it a single binary, that's still possible, but it's still another layer of abstraction. Right? If you can model with the tools that is out there, and you have a lot of choices right now. So the concurrent family of APIs and from the standard SDK, you have concurrent hash map, concurrent link queues, and things like that. You can use them. You can, let's say, if you want to do something really fancy. Nitin Bakart is again a performance lead engineer from Azure, has an excellent a queuing library called JC Tools, or JC stands for Java Concurrency Tools. You can use that. In case if you have a map scenario like what he mentioned, you have a choice of distributed non-blocking hash map. Wherever you're using a concurrent hash map, it's a drop-in replacement. You get the benefit of you can actually distribute things with it. That is from a H2O package, which is a new resource. So the point I'm busting is that if you think it has to be in memory, don't always think you need to go through a standard caching or Redis kind of a packages. You can do it in your own libraries and tools. It's still within reach. Okay. So myth 3. So if you have questions, feel free to stop. Multi-core is a silver bullet. Anything out there? I mean, I'm going to have the servers have like 36 cores now, which is standard. Maybe 105 or 6. That's also going to be standard. You pretty much solve all kind of problems if you have a multi-core machine. How many people will think that's true? Multi-core parallel algorithm is going to solve everything for you, right? Not if your system is like this, right? So if you have, I don't know, that's a tool gateway probably. Imagine the tool is your CPU. I'm going to have 100 tool gateways, that's fine. But if your system has a bottleneck here, that's going to cause a lot of contention, right? That's not going to be useful. This is not a theoretical scenario. Let's take a practical example. Let's take IRCTC booking, right? Imagine I'm IRCTC, I'm running this app on, let's say, 1,000 node machine for a hypothetical case. I'm going to book, like, what's the most famous train? I'm going to travel to Madurai. I'm booking in Pandian Express. Let's take, for example. What is it going to give you? 1,000 cores, one single train. That's your bottleneck. 1,000 threads, assuming it's not doing hyper-threading or anything like that. One core, one thread, one person can be parallel, not concurrent. One thread can be parallel. So 1,000 people you're allowing to contend to one single train, assuming the train has, let's say, for sake of simplicity, one compartment. 1,000 people are going to contend for one compartment. No matter what you have, you are constraining because there is a contention. There is just one resource out there, right? So the point I'm making is, most of the time we are fooled that parallelism solves things, it makes things faster, efficient. That's not true. If maybe true for reading, right? Let's say that 1 million people want to check up is the train fully booked. That helps because reads are non-blocking. It's not contention. But if you're trying to book a ticket, that's the right path. You have a resource contention in place. For scenarios like that, it's better if you embrace single writer principle. What it really means that if you are on a right path and on a contentious resource, just use one single thread. One thread is going to be far more effective than multi-threaded programs for a right scenario. Right? There is also a paper called Cost. Cost stands for configuration that outperforms a single thread. This is from Microsoft. They did a research, and what they found out is that if you are throwing multiple cores to solve a problem, the cost is that for to outperform the performance of a single thread, you need something like 32 to 36 threads to outperform what a single thread does. That's the amount of overhead, parallelism, and coordination brings in. Right? You can go read up that. Any questions so far? All good? Right. I have this picture. Let's say that there is just one thread, right? So you can't do too much. You need to talk to another thread, inter-process communication, inter-thread communication, whatever you want to call it. But let's say someone is going so fast and the other consumer is slow. You can think of, okay, some single writer thread is exposed to the web and people are going crazy and booking so fast. Okay? I'm not going to commit to the disk. I'm going to put the request to the queue and let some consumer consume from the queue. He's going to write to the disk, right? I have the state maintained in memory, some kind of map, whatever I want to call it. Your write path which hits the your database is going to be slower. It's not going to be as fast as your read path is going to be slower than your write. Then it's going to be a picture something like this. You're going to be drinking from a fire hose. That's not going to work. Am I making sense? Is this? So this is where queues come in. There are, like I said, multiple choices are out there. If you've heard of queue like a disruptor, it's actually an open source component from a company called LMAX. They use this in their trading app, right? So basically, single-threaded writers, but multiple consumers. How do they talk to each other? They use the disruptor to talk. What it basically is a ring buffer, a really large ring buffer. You pre-allocate the objects, so there is no allocation that happens when things are sent to the queue. What it means is that the whole thing can be garbage collection free, right? If you want a highly responsive system, no matter how much you code, there will always be GC passes, right? It's not just in Java. In any VM that is garbage collected, you will have a GC pass. To avoid that, a technique is that you never allocate on your critical flow. You pre-allocate things. Right? So ring buffer follows that paradigm. So you can have a producer and a consumer, and consumer can go independent of the producer. The only time the consumer will block is the producer has gone all the way here and is waiting, and the consumer hasn't even consumed the first message. That's very unlikely. If that happens, then things will block. It's unlikely because the ring buffer will be very, very big. You can tune that as big as you want it. Right. Okay, so the fifth myth is that anyone recognize this picture? So this is a picture usually used in, you can see this in the internet for people complaining about compilation time. Right? I just changed it for a GC pause. So if instead of people, that's a system. If a system is slacking, that's because some GC pause is happening. Should I explain what a GC pause is, or people know? Okay, don't. Okay, so let's say that you're allocating and you're using some memory, and at regular intervals, the VM has to reclaim the things that are, let's say, if you've allocated an object, there is no one referencing that object. That object is a zombie object, right? But someone has to reclaim that memory. If you're writing in C, you will allocate and deallocate, and that's the responsibility of the programmer. But if you are having a VM like Java or any other high-level VMs, the system will do it for you. The system in this case is a VM will actually keep reference counting and say, okay, these objects that are allocated in the heap is no longer accessible by any object, and hence I can reclaim the memory, right? So when this is actually happening, your application has to be stopped because you can't change and move the memory when the application is running. So what ends up happening is that you will have a pause. No matter how you write your application, when a GC happens, this is what people call stop the world. You will always have stop the world process. Right? And so even it's very important for you to know what does a GC cost and why is it cost. People most of the time the common understanding is that GC cost is the only stop the world scenario. But it's not true. Right? Um, there are scenarios like de-optimization. So in previous talk in GeekNight, I spoke about what is a de-optimization. If you want to know more, you can listen to the talk by I think by Douglas on JVM mechanics. He talks in length about what is de-optimization. Basically, if your compiler has made choices and if those choices are invalidated, it has to throw away all the compilation and has to compile again, right? On scenarios, it's possible that it has to stop the world before course correction. So from the compiled hotspot code, it will fall back to an interpreted code. So at that time, a pause does happen. There are also pause happens. Let's say if you have a piece of code and you are synchronizing a method, but for some reason you started with a single thread, right? Compiler will think, oh, there are no two threads, there is no synchronization needed. But the moment the second thread starts kicking in, this is called lock unbiasing. So it will say, oh, I need to stop the run, I need to change the code. Things like that happen. There are many other scenarios in which a stop the world can happen. So you really need to watch out for when you are building a really responsive systems. You need to watch out for these processes. Okay, so I have this. Any questions so far before I move on? On to 5. Is it? Right. The sixth myth is let's say we have Redis store or a JSON or a map. Right? What do you store in Redis? What do you typically store? Redis, memcache, whatever it is. Key values, and what is the value in most of the times? Some kind of a JSON or some kind of a message structure. Uh, so, so I asked this question. So if I'm in an interview and I'm asking this same question, I'm going to say, so if I get an answer like JSON, I'm going to think twice, right? So, is there anything else? Can you improve the state? Let's go back to the IRCTC example. Let's say that I'm giving you a map of which seat is taken and which seat is not taken, and seat have number, right? How would you store this? Yeah, but that's not the first answer, right? The first answer will always be I will have a map of JSON. True, that's very true, right? So for an yes or no answer, please resolve to bitmap. In an interview, that's how we will answer. But when you code in a real app, you will always fall back to JavaScript or JSON, right? I just have the slides over. Yeah, so in Java, you have a brilliant support for bits called bitsets. You can manipulate a bit. You can stream the bitset back. I think it's order of magnitude faster, more efficient in time space than in JSON. Whatever JSON library you use. Right. So I have this slide for the very same reason. This is again, when we are detached from the problem, we will go for an optimal solution. But when you're in the context of building an app, this Captain Obvious syndrome kicks in where you say, keep it simple, stupid, kind of a syndrome, right? Let's say, I had the same bias. Like, let's say if you have a scenario where you're keeping things in keys in memory store. The keys, for some reason, has to expire. How do you write this process? You are responsible to expire keys. Let's say I have 1,000,000 keys in my store. How would you expire? What would you do? Sorry? I can't. Batch expire. No, I mean, I'm asking you. Tell me not the code, the logic. Batch is just a word, means nothing. How would you know which keys are expiring? Yeah, Okay, that's for granted. Keys, you know when keys were inserted. You also know that I need to expire after some time, right? Nobody expires. Yeah, that's my Captain Obvious solution, right? So it's very simple. I have n keys. I will iterate n number of times. I'll check each, key is okay. This is expiry. No, yes, no. Answer. Uh, but if you just push yourself a little bit further, you can have an algorithm that works in order of one, which is a constant time, right? Can you spend a minute and think: is it possible? No matter how many keys that you have, if you go through a for loop, that's an order of one complexity. If I have a million keys, it's order of million. Yeah, that's again sorting. So I don't mean to actually come up. I don't expect you to come up with the logic. So the thought process that don't fall to the trap of let's keep it simple. Let's do the most obvious thing. You need to resist that temptation if you're really building a highly responsive system. Uh, so all I did was like push myself. How does Memcache or Redis, guarantee order of one expiry? They solved it very simply, saying when you're inserting, they have buckets. The buckets are by time. In those buckets, they'll put the key IDs. So every second the loop comes that dequeues. The moment you dequeue, it knows what IDs has to be expired. It will expire. If the expiration process is not completed within the time, the keys in the same bucket expire in the next one. You get it. So it never scans your whole set of keys every, let's say, any second. It doesn't do that. Uh, so I'm saying this is not complicated. There is no complication in implementing this logic, right? All you need to do is resist the temptation of doing the most obvious thing that seems to be correct. Okay. How many of us actually measure how fast your system is? Has anyone used Apache Bench before? One, two. What do you think? What do you test your code for? Nothing wrong. So Apache Bench, it's basically designed to test your static pages. If you're writing a platform API, it's not actually designed to test that. So there are few tools out there. For example, Gatling is really good tool. So if you're using Gatling, you make the right choice. JMeter, not so good. Um, there are also other lightweight tools like WRK and WRK2. Um, so I just came to know about one problem in all the benchmarking tools. So you have to watch out for this called coordinated omission, right? It's again a little deep topic, but I would encourage you to go read up. What it basically means is that your system, which is getting measured, is actually in coordination with the system that are in the ecosystem. For example, if you're writing a Java app or any kind of an app that's running on the OS, if the system below that freezes for whatever time, then all the tools that are out there, the number that is reported is wrong. Is because if you're taking a timestamp, the whole system freezes. There is a problem with that. So yeah, so the topic is quite complex. So, but I would encourage you to go read that. Gathering is one of the few tools that has actually fixed the coordinated omission problems. So in that way, it's pretty good. I don't know. Tell me what is that? Yeah. Yes. Okay, so if you're for whatever reason, if you're doing a micro benchmarking, which you should be doing if you're doing a responsive app, um, so there were multiple frameworks out there which really pissed off few people who wrote the JDK. There is this GeekNight, which is kind of now a standard for micro benchmarking. This is from Oracle. That's pretty good tool. I would encourage you to go there and Google it. With the basic few annotations, you can annotate what method you want to benchmark, and this tool will go ahead and benchmark and tell you, how much throughput your code has. And if you're ever thinking of plotting in a histogram, what is your response time? The tool that you should be looking for is a HDR histogram. The benefit with this tool is that you can vary how much of a percentile that you want, only dependent on how much of data you have. So if you want 10 nines, you can get it. If you want 200 nines of percentile, you can get that. As long as you record the data at that level, you can plot in a histogram. So clean code. How many of you know or aware of clean code? Clean code. Why clean code? Okay, so when I say clean code, what comes to your mind? Yeah, readable. Yeah. That's like I think like 100%. I can say that that's the reason why people push, right? The code is read more than written, right? That's true. What I want first is it's not only true for humans, it's also true for the machines. Um, so if you actually think of what JVM does for you, is that if your code is highly readable, which implicitly means it's kind of small, it's a fair assumption to make. So if you have a really small, clean code that does only one thing, the JVM will actually reward back. How is the reward back? It will actually inline the code for you. Inlining, you can think of some of all optimization, the mother of all optimization that's out there. Right? Only when you inline, it can do unrolling. A lot of things are possible only when the function calls are getting inline. If your function is not capable of inlining, you're throwing away a lot of optimizations. Right? So if you have a really clean, small code, there are high chances that it will get inlined by the JVM hotspot. Right? And it will naturally be faster. I'm just saying it helps. So if you think it's only for readability, that is wrong. That is the point that I want to make. If you have a small method, they are candidates for inlining. If you have a large method, and that's called crazy number of times, yes, JVM will compile that for you. But that's compilation, that's not inlining. You will still have the cost of calling the function, parameters, push pop, all that will happen. But you will lose the benefit of inlining. It does not inline. Because it's too big. If a method is too big, it doesn't inline. Right. So the last myth is that so the building responsive systems has got nothing to do with languages. So if you think that's the word, like you can put like 100 bold, font for the word just. If you just think, I will pick the right language. Let's say Erlang. Let's say whatever Scala, and my system is going to be super fast because I picked the language that is really fast. That's the wrong argument. So your language or your VM can only go so far. Right? That's the myth I want to bust. So there are, if you research about, there are only so much if you can do if your response time, let's say, is about less than 2 milliseconds. Okay, fine. If you want to consistently, guarantee that it's, let's say, 400 to 500 microseconds, there's nothing much you can do with your Java. The pause in your Linux kernel will be much more than a 500 microsecond. Okay. There was even a blog from the maintainers of LMAX saying that the low latency hardened version of Ubuntu is slower than the normal version of Ubuntu. They had issues. So all I'm saying is you need to look at your BIOS, you need to look at your OS, you need to look at the entire stack if you really want a highly responsive system. You can only do so much in your language, and after that, the whole ecosystem plays. Yeah, this is one of the things from It simply says that Java is one of the most is the one of the worst language with the best toolset, right? That's one of the reasons why most of the cool high-tech, high-end, low latency apps are actually built with Java. It used to be built on using C and C++. Right now, Java is the choice. Right? Just I have that for a summary. If I have questions. It's JVM. For what? The choice of language? Usually Java. Yeah. Yeah. So Java is the new C as a talk. Yeah, the coordinated omission. So AB, okay, so the problem with AB is that beyond a point, you'll be testing the bottleneck of AB than your app. Let's say you're issuing 100,000 requests a second, it's more likely that you're hitting bottleneck in the code of AB and not in your app. So you can use WRK. That's so it goes down to how lightweight and how much the engineering has gone into the load testing. If you talk about HDR histogram, um, so Gil Tene is the author of HDR histogram. He is talking about uh, the overhead of the HDR histogram is in the order of nanoseconds as opposed to even microseconds. There's literally no allocation that happens in HDR histogram. So the code is so lightweight. So you should be using tools that doesn't come in the way when you're measuring things. Right? Um, One thing that I don't think I've mentioned in the slide is if you're profiling an application, if you're using Visual VM, it's most likely that Visual VM is introducing many processes when it's actually collecting stats. That's true and it's proven. Right? There is a Honest Profiler now that I believe is the best in the lot. The name is Honest, so it is honest with that. The way it profiles is the overhead of profiling is so low, and is probably the lowest of all the profilers that are out there. Yeah, almost all the tools have mentioned all of these. So okay, so the process, if you look at the optimization the compiler does, it builds on top of each other. Let's say that I have a huge code block. If there is a function that gets inlined, then the base function's code is bigger, right? So if there is a loop that is inside, maybe you can think you're using variables that are not needed. It will do variable deduplication for you. It can also do, okay, you're computing something inside a loop that never changes. It can unroll your loop for you. All these things won't work or the compiler won't apply if it is beyond the boundary of a function call because there's only so much it can collect statistics on. That is why inlining is the mother of all optimization, is that only if that happens, multiple things build on top of each other. Otherwise, I mean, you're leaving it to other parts of the optimization that will work for you. So if you open any long, so yeah, people trade off between long functions and short readable code. If you think having multiple functions is going to come in the way of performance, that's wrong because the compiler will optimize for you. Thanks for creating. Unless any questions. Good.